Chapter 11, having finished tests for quantitative data, we're now looking at the one test that will be the one type of test that's going to be available to you on the AP test for categorical data. Recall back when we looked at two-way tables, when we looked at bar graphs, and we would compare the percentages in the categories in the bar graph, and we'd compare and we'd try to make some kind of decision if we thought there was a difference in the different groups, different categories from our two-way table. But now we actually have a formal statistical test called chi-squared tests. They are divided into what we're going to be doing today, which is the chi-squared goodness of fit test. So a lot of times abbreviated as goodness of fit. And then next class in 11.2, we'll be looking at chi-squared test for homogeneity and a chi-squared test for association independence. And those two tests are actually done in the same manner. It's just the wording of their hypotheses and their conclusions that are different, but so they're the same. But the goodness of fit test we're doing today, and you might have seen these tests if you're taking AP Bio. This is a very important test for AP Bio, and so we'll be doing it on steroids, as we like to do in AP Stats. Okay, Mars Incorporated makes milk chocolate candies, and so this is what their customer affairs department says about the distribution of milk chocolate candies. They say that there are 13% of browns and reds, 14% yellows, 16% greens, 20% oranges, and 24% blue. And then someone goes out there and they get a bag of candy, and they count it was 60 candies in the bag, and they counted how many of each of the colors came up, and this is the result right here, what they got in their sample. I don't know if they were really being random about it, but I think it would be reasonable to say that some bag from a store might represent, in general, represent Mars candies. So I don't see any clear violations of randomness there, and I wouldn't stress it overly. But so when they went out and they did this, from our procedures before, we probably would have looked at the proportion of one of the colors, like blue M&Ms, and seen that our sample statistic came out as 0.15. And then we probably, in the past, using the procedures that we did in Chapter 9, where we were doing tests of proportions, we probably would have written our null hypothesis and our alternative hypothesis, and then we would have tested our statistic against the believed parameter values. And we would have drawn a conclusion, and we would have made a decision about the blue candies. But the problem is we have all those other colors. We could perform additional significance tests, one for each of the colors, but what happens, how do we use this? It becomes overwhelming when you're going to have 6 tests, different results potentially. That's not thing. So like if you were to do that, a one sample z-test for a proportion, that's really inefficient, and it would lead to multiple comparisons, some rejecting, some not rejecting. And so that is not helpful. It would not, more importantly, it would not tell us how likely is it for us when we get a random sample of 60 candies that we're going to get a random sample of 60 candies where the colors differ as much from what was claimed by the company as this bag does, taking all the colors into consideration at the same time. That's what the chi-squared test is. It takes this one sample z-test, which only looks at one thing. How different is this one thing? But what the chi-squared does is it takes all the proportions and compares them, the expected counts to the observed counts at the same time to see what's the level, having a level of that much difference, how likely is that to happen as a result of chance behavior. So we call this, today we're working on the chi-squared goodness of fit test. And if you were writing a chi-squared null hypothesis for the goodness of fit, you would be talking about there'd be a proportions for your categories. And so in our situation, the company's stated color distribution for M&M's milk chocolate candies is correct. That would be the null, because you always give them the benefit of the doubt. Then the alternative hypothesis would be that it's not correct. If you wanted to write it with the proportion symbols, this would be an appropriate way to write your null, would be saying what all the proportions are. And this is kind of a helpful way so that you can see what proportions you are testing, you are looking at and examining for validity. And what really needs to happen is just one of these proportions needs to be enough off that it's going to throw the whole bag is going to have more variation than what would have been expected for chance variation. So the idea of a chi-squared test is that we're looking at observed counts and we're going to compare them to expected counts. And when we do that comparison to the expected counts, you want to make sure that you keep your decimal. If you expect 2.2 red M&Ms, then you should say you expect 2.2, not 2, 2.2. So keep decimals on expected counts. There's going to be a lot of calculator use for this. In general, if your expected counts, they're going to be obtained by multiplying the proportion for the population distribution. For example, we had 24% blue. We're going to multiply that 0.24 times the sample size of 60, and it'll tell us how many blues you would expect. If there were 24%, how many blues would you be expecting out of a 60 candy bag? Here's where we show our conditions for the inference. And as you can see, that for goodness of fit test, the chi-squared statistic compares the observed and the expected counts. Don't try to perform calculations with the proportions themselves. You need to have the actual counts. And then this condition, the second one, I don't know how well you can see this on the screen, but it says basically that you need to have what's called the large, I call it the large enough condition. So you need to have a large sample size, and by that they mean that the expected counts need to be greater than or equal to 5 in a category in order to do this. So that's not a normal check, it's a large sample condition check. So not normal, not normal. Okay, so cross that off. It's not normal, instead it's large sample, so that's how that's changed. Okay, our degrees of freedom is going to be our number of categories minus 1. That's the degrees of freedom. And so if we can meet our conditions for inference, then we will be able to do our null and our alternative, and we'll be able to test those, and we'll see if we have a large enough or a small enough p-value that we have the evidence that it's true, so that we're rejecting the null. Okay, and here's the chi-squared test statistic. This is on the formula sheet. Okay, and there's the formula. And so think of your chi-squared as being the measure of the distance of your observed counts from expected counts, and then they've added them all up. All added up. So they've added up all those contributions, those chi-squared contributions, and so having a lot of difference is going to give you some evidence that that it would not be expected to occur just as a result of chance variation. Okay, so chi-squared distribution for the chi-squared statistic, as I said, it's not a normal distribution. Never say that it's a normal distribution. It is a right skewed distribution, as you can see. And so if we find the sum of all the contributions of chi-squared from each of our categories, when we get the sum, like let's say that sum was 9.0, let's say. So I can put my 9 on that chi-squared measure, and I would be looking for evidence. My p-value would be the area under the curve at this, wherever my chi-squared was, and it would be the area to the right. So you're always doing the right to see if you have enough evidence to reject the null hypothesis. And so you can see how that curve changes for the different degrees of freedom, and that degrees of freedom is based on the number of categories that were in your that you were dividing your data into. And so a chi-squared test, looking very similar to the tcdf command, you're going to have your test statistics. So the probability that my chi-squared would be above a 9 would be, I would put into the calculator under the chi-squared CDF command, I would put in a 9, because that would be the value on the left, and then I would have some value that was very, very large, and so maybe like 1,000, and then whatever the number of degrees of freedom you have, and the calculator would find the p-value for that area. I've set it up in a table. We have random. They said it was a random bag. Independent. Let's check that. 60 candies, because that's N, less than 10% N. If more than 600 candies, seems reasonable. Candies. Ah. And then the next check is going to be not the check we used before. It is the large enough check. And so how do we check that? We need to know if the expected counts are they greater than 5? I don't know. Let's find out. We got to do those. So I'm going to get my calculator. I've already entered the observed values in my calculator, and I've entered those into L1, and I've actually already entered into L2 of my calculator. I've entered the percentages for that were told to me by Mars Candy. What they said were what they believe are the true percentages: 24, 20, 16, 14, 13, and 13. Those are all in my calculator. I've put those observed values in L1, and I've put the proportions that were reported by Mars Candy, which is going to be our expected values. I put that in L2. You cannot use the proportions to do this calculation. You need the actual expected count. So I'm going to go to the top. You can see that I'm at the top on the L2. I now have it on large screen too. And I'm going to say that I want you to take those L2 proportions and multiply by 60. And because I'm keeping myself in L2, it's going to overwrite L2 with the expected counts. Enter. Those are the expected counts. I will leave those decimals, and since I have them in the calculator, that's preferable because then the calculator knows what the decimals are. Those decimals are important. It is not correct to round that first one to 14. You need 14.4. Now, in L3, I'm going to find the chi-squared, which the formula is on your formula sheet. The formula says that I will take my observed count. So notice I'm at the top on L3. I'm opening with a parenthesis. I will take my observed count, which was my L1. I will subtract my expected count, which is my L2. I will close my parenthesis and square that quantity. Then I will divide by, look at the formula sheet, know which one you need to divide by. It's the expected L2. Enter. These are the chi-squared contributions that together make the deviations from the observed from the expected, and we're looking for, are these together? Together, are they enough to reject the null hypothesis? So I'm going to now go out of this, and I'm going to find out what the sum of those chi-squareds are. So by going to my one var stats, and in this software package, it doesn't walk me through the list, but I need to add the L3 list. So when I add that up, you can see that the summation with sigma, capital sigma, the summation of my x's was 10.17994505. So that's the chi-squared sum, and I'm wondering if that is enough evidence on a right tail, because remember, chi-squared tests are always looking for being further away, so it's always on the right. And so now I'm going to go into my distributions just as I would with normal CDF and T-CDF, but now chi-squared. See, there's chi-squared, a very cursive-y looking X. Chi-squared CDF. Pull that in there. Whoops, actually I don't need the second key. Let's see if it just goes in there. Okay, and then I need that. It was 10.1799 comma. It's always going to the right, so let's use a very large number so that it knows to keep going. And then I need to tell it the degrees of freedom. So it's kind of like the t-test and that you need your degrees of freedom, but the degrees of freedom is not about how many candies there were, it's about how many categories you have. So there were 6 categories, 6 minus 1 is 5. There are 5 degrees of freedom on this chi-squared test, giving me a p-value of 0.07029, so I'll call that 0.0703, which at the 0.05 level is not significant evidence to reject the null hypothesis. Okay, so percentages are not expected counts, and they want to see your expected counts. So all of these needed to be out of a 60 M&M bag, how many do you expect to be these are my expected counts, and I'm keeping my decimal. And now I am going to calculate my, well, I've already calculated those chi-squareds, and I put them in L3, so I'm just going to write down those numbers. These numbers are easy to find with the goodness of fit because they're set up right there in the calculator when you're finding your expected counts. They're right, it's really easy to do this L3. Oops, that's wrong. I wrote a 3. That L3 calculation. So the sum of my chi-squareds is 10.1799. And I had left off over here with my large enough condition. I had left off on my conditions. I'd never said if are my expected counts all greater than 5? Are they? Yes. So are greater than 5. So that's good. I have that is working. If I saw that there was an expected count not greater than 5, if, let's say, for example, I had red and I had brown, for example, let's say I had observed and I had expected, let's just say, I'll just keep the observed what they were, but let's say I expected to see 3.5 and 3.5. Let's just say my expecteds would not be greater than 5. That is a problem. So to fix this problem, I would make this one group. Let's call it red-brown. And then I would change this to being 16. And now my expected counts would actually be, well, 3.5 plus 3.5 is 7. No decimal. Now I would have, are my expected counts greater than 5? Yes. So that's the way you fix that. If you have a category or categories that are not meeting, you have to bring them together, and you won't be able to tell for red and brown separately, but you have to put them together. Okay, so my conditions for inference are met. I will do a chi-squared goodness of fit test. My null hypothesis, the stated color distributions fit what Mars said, Candy said. And then my alternative will be at least one proportion is not correct. And then you can see the wording on the other pages that were probably a little better. But my degrees of freedom, I'm not going to use 60 because that's not, it's supposed to be number of categories, not the number of candies, the number of categories. So 6, because there were 6 colors. This one is 5. So the probability that my chi-squared goes above a 10.1799, or maybe 10.18 if you prefer, is when I punch that in the calculator. Here, let me write it in red. I would have punched in a chi-squared CDF. I would have had 10.1799, comma 1,000, comma 5. And when I do that, I get 0.0703. So that is not enough evidence to reject the null. So since the p-value of 0.0703 is greater than alpha equal 0.05, we fail to reject the null hypothesis. And there is not significant evidence that the color distribution for M&Ms, for M&Ms, it almost looks like an R, for M&Ms is different from what Mars stated. And that's basically, and we're right or we're wrong. But that's what the evidence is, that there's not enough evidence to reject their claim. Okay, so now looking at Fathom software, if in your textbook there's in your textbook you have the Fathom output on page 625, and that output is looking at looking at if these proportions for the candies are true, if they're true, and in our little Fathom computer brain we're going to have them be true. Then in our little computer brain we're going to go in and pull out samples of 60 candies from all these little electronically generated theoretical candies. How many of these samples are going to have differences, collective differences of all the colors taken together from what the company stated? How many of them are going to have this collective difference of a 10.18 or more? Well, if you look on page 682, you can see that in this simulation, 37 of them did that. As a result of chance variation, that's what happens. So the probability from the simulation, that says that 37 out of 500, they got a probability of 0.74, which compares very nicely to the probability that we just found using our chi-squared distribution, using our chi-squared test. So if that 0.074 empirical probability of this happening or more extreme is only, it's a very small difference, 0.0037 higher than the 0.0703 from the chi-squared GOF goodness of fit test. We could say that this has some very similar results, and so you can see how this is a very important test that can give you the evidence, or in this case, not enough evidence, to examine a situation for whether or not you shouldn't believe the original claim. So in this example, we have births. Are they evenly distributed across the days of the week? We could look at a random sample of 140 births from local records in a large city, so very large city. We are wondering if this data is going to give us significant evidence that the local births are not equally distributed on all the days of the week. So, is this random? It was a random sample. Is this independent? That's based on the N. So I'm looking at if, yeah, it seems reasonable that in a large city, we would expect over, 1,400 births in a large city. So that, I think we can establish independence in this situation. And let's see here. And in fact, actually, you could almost think that that births themselves might be independent in general. But then we need our large enough. And that's the one where we actually need our expected counts. And so we are going to be looking at our expected counts. So we actually have to counts. We have to look at them. So let's set this up. Observed, expected for the days of the week. I'm just listing out the data. And then if there's 140 births, we'd expect, if we divide that by the 7 days of the week, we would expect 20 births every day. If there had been a decimal, I would have kept the decimal, but there was no decimal. So I'm just going to put that in there. And then we can find out what the chi-squareds are from our calculator. Those are going to be our chi-squared contributions. And if we reject, we're going to want one of those. And we're going to find out what the sum of all these chi-squared contributions is. We're going to find out what that is because and I can go back. Because of this, I can go back to over here. Expected counts are all over 5. So that's good. So that's it. So we are going to do a chi-squared goodness of fit at the alpha equals 0.05 level. And so now, and my degrees of freedom, since there are 7 days of the week, and we take away 1, so 6 degrees of freedom. All right, I'm going to show you with the calculator. Okay, back to my calculator, and I have the still have the data for the M&Ms in, and I just want to show you that chi-squared, I would highly recommend you use your calculator to run the test. Whoops, what am I doing? Got to go to the tests. And so I hit stat tests, and I'm scrolling down to look for the chi-squared test, And there were two of them listed, as you can see. There's the chi-squared test, which we'll be doing next class, and then there's the chi-squared goodness of fit, GOF test, which we are doing today. I click on that. I have my observed and my expected, which you need to have set up in advance. You need to then tell it your degrees of freedom. In my situation, I have 5 degrees of freedom. You have to enter all that information yourself. You click calculate and you're done. It gives you the chi-squared sum, which confirms that it was 10.1799. It gives you your p-value, and you specified the degrees of freedom, and you also specified the chi-squared contribution. I mean, you didn't specify these. The calculator calculates the chi-squared contributions. So that's very useful. Let's use that to do this example right now. We have the births. So I'm going to go back to my calculator and clear the information that I have there before. I'm clearing all of that, and I'm going to enter the births. Clear that right there. And so I'm going to enter the births, and that is okay. So I think that's going to go in there. So I have my observed and I have my expected. And so let's click on stat tests and go down to the goodness of fit. So if you're taking AP biology, you're probably doing some goodness of fit tests, and you would use this command and you'll know all the answers. I have my L1, my L2, and I have to change my degrees of freedom to 6, and I will calculate that. And so it gives me my contributions. However, it's very tricky to see the contributions by scrolling to the right. It's hard to see the numbers and keep track of which ones they are. So I find it much easier to go into my stat edit and to actually just tell the calculator, I want to take my L1, which is my observed, and I want to subtract my L2, which has my expected, which there wasn't a decimal in this situation. However, if there was, I would keep my decimals long, and that's the advantage of using the calculator. And there are my chi-squared contributions more organized. Let's write that on the other page. Okay, I'm going to write down all these numbers as I would on my mini quiz, as I would on my AP test. Oh, that's interesting. Look, a chi-squared difference of 0, that's when it's exactly matching up. And when I look at these days, I can see some days have greater differences, greater chi-squared contributions than others. And then I need to write down what my null is. My null would be that all the days of the week have the same number of births. Same distribution of births. Well, that was kind of a long way. I could have just said probability each day would equal 1/7. I could have written my null as just like that. My null just being like that. But then my alternative would be at least one day has a different each one day is not 1/7. How's that for keeping it brief? Okay, my chi-squared was 7.6. The probability, the p-value of my chi-squared being above a 7.6 according to the output from the goodness of fit test, according to doing a chi-CDF, be that. So since the p-value of 0.269 is greater than alpha equal 0.05, we fail to reject the null hypothesis and there is not significant evidence that the births are not evenly distributed for each day of the week. And that's all I can say about that. But just to review, type 1 and type 2 error and what they mean. In this situation, because I have failed to reject the null, does that mean that the null is correct? No, it does not. We never know if the null is correct. We just cannot find enough evidence to reject it. Can we conclude that the birthday on these days of the week in this local area, that they're evenly distributed? No, we cannot make that conclusion as well because we failed to reject. Now, we may be correct. We may be correct. And that would be the births are evenly distributed. But if we are not correct, what did we just do? Did we do type 1 or did we do type 2 error? If we are not correct, we failed to reject the null when we should have rejected it. We failed to reject the null when the null was really not true. And to me, that would just, thinking about this common sense wise, and I would not write about this in my conclusion on my mini quiz, but if somebody asked me, do you feel like you may have done type 2 or type 1 error? I would say, well, given that there's C-sections, given that there's induced births, given that a doctor scheduling one of these induced births or a C-section probably would schedule it for a Monday or Tuesday, just so that then if there is a problem, the person would still be there on weekdays. Given these things, I think it does make sense that we might not have been correct. So if we are not correct and we have failed to reject, HA was true, we have done a type 2 error. We have we have just committed type 2 error because the alternative was the truth, but we failed to reject it, failed to reject the null. We failed to reject the null. HA was the truth. We made a mistake. That is a type 2 error. So just to remind you of that. Oh, and if how might we have been able to find this? Increase sample size. The answer to most all your problems, if you're having trouble finding it, then you need to increase your sample size. Okay, now we're going to do the biology example here. Last page with our biologists, and they have these tobacco plants. And so tobacco plants with their Punnett squares, they've got a dominant gene and a recessive gene, and I'm calling them capital G and lowercase g for this color. And so what happens with these plants, if you get the two dominants, you're going to have a green plant. If you have a dominant and a recessive, you'll have a yellow-green color. And if you have the two little g's, then you're expected to have an albino color. So if you look at your Punnett square here, if you look at this Punnett square, we expect each of these categories to be a quarter. So each of these comes out to be 25% or 0.25. So we're expecting a 1-to-1 ratio. 25% green, 50% yellow-green, and 25% albino. To test this hypothesis, we're going out there, we're going to have 84 plants. That's going to satisfy our, I'm just going to write them really quickly here. That's going to satisfy our independence, assuming there's more than 840 plants in the world. We're going to have to do this experiment randomly. And then because we're doing chi-squared, we need our expected counts to be large enough. So large enough a condition is important. Let's find out. Okay, so if we have our GGs, okay, 23, 50, 11, and then 0.25 times the 84, we expect to have 21 plants there. Same number down here. Just doing it by hand. These are pretty easy numbers to work with. 42. And then we would get our chi-squared contributions. This one is a reject, so we actually really are going to need these chi-squared contributions. I would go in and use the goodness of fit test on the calculator. Oh, all expected counts. R over 5. We don't have to combine any categories. If you did your chi-squared values, these are the values you would have gotten. The sum of the chi-squareds would have been 6.48. The probability of getting a chi-squared that or bigger with degrees of freedom, there are only 3 categories of plant, so degrees of freedom of 2 would have been 0.0392. Because I am going to reject, I will need to look back at my chi-squared contributions, and I will have to talk about this number in my conclusion. So let's do that. And then we go, since the p-value of 0.0392 is less than alpha equal 0.05. Did we do 0.05? Yes, thank God. We reject the null hypothesis and there is significant evidence to reject the null. Whoops, I already wrote that. There's significant evidence that, oh my gosh, I never even wrote my null and my alternative hypotheses. All right, let's write them right here. Okay, let's see. PGG equals 0.25. PGG equals 0.5. And PGG equals 0.25. And then my alternative, at least one proportion is different. Devin, that at least one plant color differs from the 1-to-1 ratio. The largest contributor was GG, or albino, plants with chi-squared equals 4.72, period. Okay, so if you reject the null and you have significant evidence that the alternative is true, you need to report the largest contributor, and sometimes there's more than one, state what it is and how much that contributor was. That is very important. If you reject the null, make sure that you are stating what you found. And there are two possible situations, just to remind you on error. There are two possible situations that can happen in this situation. We have just rejected the null. So that means that we think the alternative is true. And we've rejected the null. So it's possible that we have committed a type 1 error when the null was really true, but we rejected that fact. So